Hey folks, we're going to do an example of calculating electric potential due to a line of charge off the end. So for our convenience here, I've rewritten the two methods for finding voltage. Okay, there's one if you know the electric field and you can integrate it. The other one is if you want to consider your object as a bunch of point charges. Um, our object in this case is a line. So let's say you have a ruler or some piece of wood um, charged up, and the line charge density is lambda, so maybe it's, I don't know, 20 nanocoulombs per meter, right? And the bar has a length L, and I've given coordinates here, x coordinates. So the bar extends from -5 to -2. So L in this case is 3 meters, okay? And then A is how far off the right end of the bar we are. That's from -2 to 3, so that would be 5 meters. So A is equal to 5 meters. So we're going to calculate the electric potential, aka voltage, at that 3 meter mark over there. Okay, and we're going to first figure out which method to use, and then I'm going to show you two ways to do this. They're roughly the same, but a slightly different tweak on them. So the first thing we got to figure out is, oh, first of all, if you need a moment to copy this diagram and such, I would pause the video now and do that. All right. So the first thing to do is figure out which method to use, method 1 or method 2, to figure out the voltage at our spot there, okay? Well, if I asked you to use method 1, you could do it if you knew the electric field of a bar off the end. And we did talk about that several chapters ago, or a couple chapters ago, but frankly, I don't even remember the equation. I think I could probably write it down pretty close, but I don't remember it exactly. So I'm going to go with method 2. I'm going to make the bar into a bunch of point charges. So for instance, let's say here is a point charge right there, okay? And that charge has a charge dq, okay? And what is that in terms of lambda? Well, lambda is equal to dq over dl, or in this case, we're going to do dq over dr. Because we're going to need the radius from our point of interest to that dq. So here is your radius, okay? And dr is the difference in radius from the beginning of this little charge to the end of this little charge. So on this diagram right here, this is dr, the difference in r. Well, that's also dl, what little bit of length of the bar that we've captured with our dq. So if I write dq out by itself, dq is equal to lambda dr. Okay, and that's probably the hardest part of this problem. All right, so voltage is equal to k, the integral of dq, which is lambda dr over r. So the first way I'm going to do this, using method 2, I'm going to do this in terms of radius. Okay, so what does our radius go from? Well, the nearest point from the bar to our point is A. So I'm going to put an A there, which happens to equal 5 in this case, which, well, I'll put numbers in a moment, but it's A. Okay, that's where the bar starts. Where does the bar end? How far from this point here does the bar end? Well, that's A plus L, length of the bar, which would be 5 plus 3. It'd be 8 meters away. Okay, so then we're going to integrate. K is a constant. Lambda is also a constant, so I'll drag that out of the integral. And what are you integrating? You're integrating dr over r, which is simply the natural log of r evaluated from a to a plus l. And your answer would be k lambda natural log of a plus l, oh, and I'll put this in brackets, minus the natural log of a. And if you know your log rules, this ends up being k lambda natural log of a plus l over a. Okay, now I want to make a note here. If I gave you lambda, if I gave you a number for lambda, like 10 nanocoulombs per meter or something, you know k is 9 times 10 to the 9th. In this problem, what's a plus l? Okay, that's just a distance. Well, a is 5 and l is 3, so this would be, the numerator here would be 8, and the denominator would be how far is the beginning of the bar from our point. Well, that would be 5. So it would be natural log of 8/5. Okay, keep that in mind for this next part I'm going to do. So this last thing I'm going to do is I'm going to do the same problem, but I'm going to do it in terms of x, not r. Okay, so it's going to be roughly the same, but there's a slight and important difference. So we got k, the integral from x1 to x2 of lambda. Now instead of saying dr, we're going to say dx over, now here's where you got to be careful. So we're doing this in terms of x now. So we're calling this little distance, instead of saying it's dl or dr, we're calling it dx. It's going to be the same thing in this case. But it's still divided by radius. Well, what is that? Well, that is x minus 3. Okay, now let me explain. X1 is going to be -2, and x2 is going to be -5. Those are our two x's. So I'll write those in here. So this will be -2, and this will be -5. So our first radius is the -2. So it's -2 minus 3, which is -5. Well, does that make sense? Is this first distance, the first x from here, is that equal to -5? Well, yeah, it's to the left and it's 5 away. And our second one is -5. What's -5 minus 3? Well, that's -8. So is that second radius from our point to the far end of the bar, is that -8? Well, sure, you're going from 3 to -5, that's -8. Okay. So it's the same thing we're doing here. We're just doing it in terms of x instead of r. So you get your k lambda, and you're integrating dx over x minus 3, which is natural log of x minus 3, and you're evaluating that from -2 to -5, which would be k lambda natural log of -5 minus 3 over -2 minus 3, which would be k lambda natural log of -8 over -5, which is 8/5. So that would give you the same answer that the one in green here would give you. So there's two ways to do this. You can do this in terms of radius, like strictly how far are you from the point, or you can do this in terms of x coordinates. If they're not specifying which one, then use whichever one is most convenient for you. All right, I hope that example was helpful, and thank you very much.